Hello, my name is Ethan, and my project that I'll be discussing today is titled Lightning McQueen Goes to School, Learning-Based Autonomous Driving for F110th Vehicles. My supervisor for this project was Dr. Tran from the Computer Science and Engineering Department. And before I go any further, I would like to point out in the bottom right that this is the F110th vehicle, for those of you that are not familiar with it. To provide some motivation for this project, autonomous vehicles have an enormous potential in decreasing all vehicle-related accidents. However, before they can become available to all consumers, they must first guarantee a better safety approval rating than human drivers. For some background into this problem, autonomous driving research has been in the works for 70 to 80 years now. However, there's still yet to be any level 5 autonomous vehicles or fully autonomous. Also, with the advent of supervised learning, along with reinforcement learning in the modern era of computing, these have produced a resurgence in the field of research for autonomous driving. Also, below we have 5 of the leading companies in the field. Starting from the left, we have General Motors Cruise, Tesla Autopilot, Google Waymo, Amazon's Aurora, and Comma.ai. The main contributions of this project was lane following and advanced emergency braking. To begin with lane following, this just means the vehicle is able to stay in its position within the lane. And then with advanced emergency braking, this teaches the agent when to perceive there's going to be a crash. And if it suspects there's going to be a crash, then to apply its brakes, allowing it to stay safe. Here I have a short clip demonstrating the advanced emergency braking system in action. So this clip was done in the Carla simulation environment. The methods used in this project was a dueling deep queue network, which is an extension of the deep queue network. And this essentially takes in the state of an agent, passes it through some linear layers. A linear layer is a linear transformation. So you apply a linear transformation to the input values and you output the linear transformed values. And then on these linear transformed values, you apply an activation function, most commonly a rectified linear unit. I'm not going to get into the details of this, but this is very common in the field. And then once it's passed through all these layers, then it outputs a Q value for each action. And the Q value essentially represents how advantageous it is to take that action. So once you pass in a state, and this state has, say, 5 actions, so you have 5 Q values corresponding to each action. And through this, you're able to determine which action is the optimal action. So this chart depicts the results from the experiment. On the x-axis, you have the episodes. On the y-axis, you have the reward. So in the blue, we have the episodic reward, and this is the reward received for every episode of training. As you can see in the beginning, the range is very large because the agent is not aware which action is better. So it's just taking random actions in the beginning. And then as you can see over time, the range decreases. And then now if you look at the average reward in red, this is the average over the last 50 episodes. So it's a very smooth increase as opposed to the very large range. And by looking at the average reward, you're able to better observe the agent learning and how it's able to learn the optimal braking policy over time by reducing its punishment and in a sense increasing its reward. So now for some conclusions. This experiment or this project demonstrated that the agent was able to learn the optimal braking policy, and this was done through a reward function. This reward function heavily punished the agent when it crashed, and the punishment was increased with respect to its speed prior to the crash. This has parallels to in real life. You can think about if you crash into a car, depending on how fast you're going prior to your crash, you'll produce more damage. And this was captured with the reward function. So these contributions done in this project are building blocks to develop a fully autonomous driving system. So lane following and advanced emergency braking are two of the most fundamental things, because from those you're able to build on top of and develop more features. This was the poster that was used for this presentation, which was developed from our project. And these are my references and my acknowledgements. I would like to thank the National Science Foundation for funding this project and allowing this to be possible. And that is the end. Thank you very much. And now I'm open for questions.